Imagine you walk into a coffee shop. Your coffee costs $5, but the smallest bill in your wallet is a 20. You can't rip the bill into quarters. You hand over the whole thing and get 15 back. Bitcoin works exactly the same way. There are no account balances anywhere in Bitcoin. No running total gets updated. Your money lives somewhere entirely different. To understand how it moves, let's look inside an actual transaction. Every Bitcoin transaction has two sides, inputs and outputs. Inputs are funds being consumed, outputs are new funds being created. Think of a transaction as a box. Value flows in on the left through inputs and flows out on the right through outputs. One critical rule: the total output value is always less than the total input value. That gap is the minus fee, payment for including your transaction in a block. Let's trace a concrete example. Joe wants to send Alice 100,000 Satoshis. A Satoshi or sat is the smallest unit of Bitcoin. 1 Bitcoin equals 100 million sats. Joe constructs transaction 1. On the input side, he provides 105,000 sats from a previous transaction he received. On the output side, he creates a single output, 100,000 sats locked to Alice's address. The difference, 5,000 sats, goes to the miner as the fee. Nobody writes the fee explicitly into the transaction. It's simply whatever input value isn't accounted for in the outputs. If Joe accidentally left 50,000 sats unassigned, the miner will collect all 50,000. Inputs must be fully consumed. There are no refunds for mistakes. What happens when the input is bigger than what you need to pay? Return to the $20 bill. You hand the cashier a 20. Coffee costs $5. The cashier gives you $15 back. Now map this onto Bitcoin. Alice received 100,000 sats from Joe in transaction 1. She wants to pay Bob's store 75,000 sats. Her input is that full 100,000 sat output. She cannot spend part of it. The entire output must be consumed. So Alice creates two outputs. Output 0, 75,000 sats to Bob. Output 1, 20,000 sats back to herself. That's her change. Now let's check the fee. Total inputs equal 100,000 sats. Total outputs equal 75,000 plus 20,000, which is 95,000 sats. The remaining 5,000 sats become the fee, since fee equals total inputs minus total outputs, which is 100,000 minus 95,000, giving us 5,000 sats. Here's a key insight. At the protocol level, the payment output and the change output are structurally identical. Both are simply an amount and a locking script. The network cannot distinguish which is the payment and which is the change. Now let's zoom out and see how these transactions connect. Each input points to a specific output from a prior transaction using two pieces of data. The TXID, a unique 32-byte hash that identifies the source transaction, and the position index, a zero-based number specifying which output within that transaction. In transaction 2, Alice's input references transaction 1, output index 0. That's the 100,000 sats Joe sent her. Now Bob holds 75,000 sats. He creates transaction 3, one input referencing transaction 2, output index 0, one output of 70,000 sats to a recipient, 5,000 sat fee, 3 transactions linked into a verifiable chain of ownership. So far, we've seen tidy examples. Real wallets face messier choices. Suppose your wallet holds 4 unspent outputs, 10,000, 25,000, 50,000, and 80,000 sats. You need to pay 60,000 sats. Coin selection is the wallet's algorithm for choosing which outputs to use as inputs. Let's compare two strategies. Strategy A, pick the single 80,000 sat output. One input makes the transaction compact and cheap in fees. The change is 80,000 minus 60,000, which equals 20,000. Sats returned to you. Strategy B, Combine the 10,000, 25,000, and 50,000 sat outputs. Together, that totals 85,000 sats. The change is 85,000 minus 60,000, which equals 25,000 sats. Notice that strategy B actually produces slightly more change than strategy A, not less. But the real trade-off is this. Strategy B uses 3 inputs, making the transaction larger in bytes, which means a higher mining fee. On the other hand, strategy B consolidates 3 small outputs, tidying up your wallet for future transactions. Every wallet navigates this kind of trade-off automatically when deciding which coins to spend. These choices produce a handful of recognizable transaction shapes. First, the simple payment, 1 input, 2 outputs, payment plus change. This is the everyday purchase. Alice pays Bob and receives change. The majority of Bitcoin transactions follow this pattern. Second, consolidation, many inputs, 1 output. Imagine exchanging a pocket full of small coins for a single large bill at the bank. A wallet does this by sweeping many small unspent outputs into 1 large output. This reduces future transaction costs because later spending requires only 1 input instead of many. Wallets often consolidate when network fees are low. Third, payment batching, 1 large input, many outputs. A cryptocurrency exchange processing withdrawals for hundreds of users packs them into a single transaction. 1 input funds dozens of outputs, each going to a different recipient. Payroll works the same way. 1 funding source, many employees paid simultaneously. Batching saves fees because a single transaction with many outputs costs far less than sending many individual transactions. 3 different shapes, same underlying rules. Inputs are fully consumed, outputs are explicitly created, and the difference is always the fee. There's one more consequence of change outputs that most people overlook. Privacy. The payment output and the change output look identical on the blockchain. But if Alice sends change back to the same address she's already used, an observer checks which output address has appeared before. The reused address is obviously the change. Now the observer knows the other output is the payment and can deduce exactly how much Alice spent. The fixed wallets generate a fresh, never before used address for every change output. Both outputs now go to new addresses. An outside observer sees 2 unknown addresses and cannot determine which is payment and which is change. Bitcoin has no running account balances anywhere. Your wallet's balance is the sum of unspent transaction outputs, formerly called UTXOs, that your private keys can unlock. Each UTXO sits on the blockchain waiting to be consumed as an input in a future transaction. Every transfer consumes whole outputs, creates new ones, and extends a chain of cryptographically signed handoffs. No central authority maintains this ledger. Any participant can trace any coin's lineage all the way back to the moment it was first mined. Next time someone tells you they sent Bitcoin, you'll know what happened. They consumed the bill, created new ones, and extended a chain that anyone can verify.